Hi, a very good morning and warm welcome to all to DVCon India 2021, specific to Track 2 tutorial session. I'm Karthikeyan Subramanian from Qualcomm, and I will be taking care of this Track 2 tutorial moderator role. And starting from day one, which we have the great keynote on intelligent edge, era of smart concurrence and system verification, how the solving edge computing complexity. It was wonderful keynote from the keynote people, and we do have the interesting panel discussion as well. Continuing the futuristic and efficiency trends of verification, this tutorial session focus on achieving faster regression throughput by applying machine learning and advanced technologies. This tutorial session is going to be presented by Anchal Shasteva and Ankur Jain from Cadence. Thanks to both of them. I would like to give a quick introduction about them. Anchal Shasteva, a senior principal product engineer at Cadence Design System, has 14 plus years of experience in EDA industry. And SOC design and verification of multi-core SOCs, she has that experience. She has already worked earlier with the mobile SOC verification team. She holds a master degree from microelectronics from Punjab University. Ankur Jain is senior product marketing manager at Cadence, has more than 18 plus years of experience in different marketing and engineering roles. He has been driving successful marketing campaigns for leading EDA products. Earlier, he has worked with the processor and SOC design and verification teams, developing expertise in system Verilog and UVM processor architectures as well. He holds a bachelor degree in electrical engineering from NIT Jaipur. So thanks to both Anshul and Ankur who will be presenting this tutorial session to us. A request to audience, post-tutorial, audience can post their questions in Q&A chat box so that we can moderate to get that answers from authors appropriately. Once again, warm welcome to all to DVCon India 2021 and this productive tutorial sessions. And over to you, Anshul and Ankur. Thank you.
Hi, good morning everyone. Welcome to this tutorial by Cadence Design Systems. Our topic is achieve faster regression throughput by applying machine learning and advanced technologies. Myself Ankur Jain. I work as Senior Product Marketing Manager at Cadence. My co-presenters are Achal Sachdev, Senior Principal Product Engineer, and Sundarajani, Senior Principal Application Engineer. And our agenda is, we'll go through some overview of regression throughput, and we'll see various technologies that can be used to improve the regression throughput. And the main focus area of this tutorial is going to be machine learning. How you can apply ML to optimize your regression and achieve your verification goals faster. We'll also showcase some case studies and we'll present some results, which is based on our experience of working with top semiconductor design companies and how we have helped them to apply these technologies and ML to really get significant improvement in regression throughput and overall verification turnaround time. And we hope that a key takeaway from this tutorial will be that you can go back to your verification projects and you can plan to apply the same technologies and ML to achieve your verification goals faster. So with that, we start with this tutorial. We all know that we are going through a big wave of innovation. It's actually disruptive. It's disrupting all aspects of our life. And pandemic has increased that disruption. In fact, pandemic disrupted our life, and I see that as a silver lining, that the disruption which pandemic has caused actually has increased the speed of innovation also. In 1960s, the innovation was being driven by Moore's law in semiconductor and system design. And in recent years, we have been hearing about slowdown of Moore's law, but the innovation continues. And EDA has always been an enabler of innovation in semiconductor and systems. And whether we talk about 1960s or current era, EDA is keeping with the pace of innovation in semiconductor and systems. If we look at the big innovation waves that we are experiencing, these are, we can name some market segments like 5G or cloud or automotive or consumer electronics or healthcare and medical systems, but it's everywhere. And one common theme across all these innovations is artificial intelligence. AI is penetrating everywhere and changing the way we look at things, we develop and design things, and we actually consume the things. So data and AI is penetrating everywhere, and EDA is not behind. In EDA also, we have seen a lot of innovation in recent years. Some of the key innovation areas which we can talk about is like parallel and distributed computing across all EDA tools, or full flow solutions where which can increase your performance and productivity multifold. And the most important game-changing technology in EDA is also machine learning. So machine learning can significantly improve your overall verification turnaround time, or it can change the traditional way we have been doing design and verification. We know that the complexity of SoC is increasing exponentially, and there is a constant pressure to complete your design and verification at a faster rate. There is a constant pressure to improve performance, productivity, and overall turnaround time for chip design and verification. And that's where EDA and specifically these technologies, and most importantly, the game changer is going to be machine learning. So when we talk about the constant pressure on overall verification turnaround time, to shorten that verification turnaround time, we can think about a lot of technologies which can improve your performance, productivity, as well as regression throughput and overall verification turnaround time. So to start with, there are a lot of build technologies like parallel and incremental build. We can reduce the build time significantly and jumpstart the actual simulation, actual verification faster. Then there are a lot of test cases which has long initialization routines like reset or link up, and all these initialization routines are repeated in each test case and consumes a very long, significant portion of overall simulation time of a particular test case. We can use save and restore. What can be done is you can run these init portions only in the base test case, you can save it, and then you can restore it back. Using save and restore this way, the init sequence is run only once in a test case, and all in subsequent test cases, it is just restored, saving significant time in all those test cases and reducing your overall regression time significantly. Then there are certain test cases which are very long running. These test cases are so long running that your all other ways of optimizing your simulation time, your optimizing your regression time is still not improved because of these long running test cases. So what we can do is we can leverage the multi-core simulation engines to accelerate these long running test cases. Then there is verification management. You can use various techniques like ranking and coverage correlation to achieve your coverage goals faster and improve your overall regression throughput. And as we have been saying that the main focus area of this tutorial is machine learning. So in machine learning, you can apply ML to your original regression and you can generate a learning model. That learning model can identify the hidden pattern in your random verification, and it can create an optimized regression out of it. That optimized regression will take lesser time but achieve the same coverage goal while keeping the random behavior of the test bench. We'll go through more details of all these aspects of ML, how it is applied, how you learn through your original regression, how do you generate a new optimized regression, and finally reduce or shorten your overall regression time. Then there are certain other use cases also. ML will go through that also, like you can target a particular coverage space, or you can use it for bug hunting also. And this is definitely one of the key technology that can reduce your overall verification turnaround time significantly, even by 5x factor also. Now let's talk about build technologies. So what is parallel build? you have you can divide your design and test bench into multiple portions, and you can create all these snapshots. You can build all these snapshots in parallel. Now suppose you change one portion of your design, the code changes of one portion of your design. You need not to recompile your entire design. You can just recompile that particular snapshot, and that's what is incremental build. So you can use parallel build and incremental build to significantly reduce the build time. Then when we move from IP verification to SOC verification, there is another interesting technology called hierarchical build. You can build all your IPs in a hierarchical way, and you can reuse the same build at SOC level. So this can again save significant time. Obviously, it can save build time as well as it can reduce the memory and disk space also. And then in certain scenarios, what you can do is you might have multiple flavors of your SOC. Now, while using this hierarchical build, you can create different configurations of build, basically build for different configurations of your SOC or different flavors of your SOC. And you can run all these flavors of SOC, the regression for all these flavors of SOC in parallel using hierarchical build. And that certainly improves your regression throughput. Now, multi-core simulations or multi-core engine to improve or accelerate the long-running test cases. As we say that your chain is as strong as the weakest link of the chain. Similarly, you can say for regressions that your regression is as long as the longest test in your regression. Now, sometimes these long-running test cases can really be the bottleneck of your regression. If you see in this scenario, all your test cases completes much faster, whereas there are few long-running test cases which are taking much longer, and that's where your overall regression is taking much longer to finish. You can leverage multiple cores of a server. You can use a multi-core simulator, and you can divide these long-running test cases across these multiple cores, and you can accelerate these test cases, and your overall regression time reduces significantly. So now over to Aanchal to go through details of save, restore, verification manager, and machine learning. Over to you, Aanchal. Thank you.
Thank you, Ankur. Hello all. So I'll cover some technologies, flows like save, restore, ranking, and correlation, and machine learning flows that can help improve regression throughput and performance. So I'll start with save, restart first. So yet another way that users can improve the regression throughput is by using flows or methodologies like save, restart that can help save some of the common initialization times that their regression test would have. So saving that initialization time across all the tests will significantly improve the regression throughput. So users can save the simulation to an interesting functional point, and other tests in the regression can restart the simulation from there and save on that initialization time. So this flow is mainly helpful if there is a long initialization time for your test and a relatively shorter test time. Another advantage of using this application could be in debugging failures where you have to reset your simulation to time 0 and start debugging from there. Rather, you can save the simulation at specific cyclic points, and while debugging, instead of starting from 0 every time, you can just start from those specific checkpoints. Of course, there's a trade-off here with respect to the disk space. So here I've shown an example on how do we set up for save, restart. You can run the simulation to a specific checkpoint, save the state, and then you can restore the simulation from the state, and then you can run either a new sequence, a new seed, or even the same seed. Right. So the next thing which I'm going to talk about is ranking and correlation. So you can improve your regression throughput by ranking your runs and dropping the redundant runs that do not add significantly to the coverage grid that you may want to achieve. On a high level, you can say that ranking helps you identify the runs that makes the most efficient test suite for regression testing and eliminating any redundant runs. It also helps in achieving the target coverage goal faster. Also, you can correlate the runs or test with required coverage grid and attributes and see where you can improve upon and add more if needed. Okay, so the next is machine learning applications that can help you improve the regression throughput and performance. Generally, the manual process of identifying or debugging the coverage holes takes a whole lot of iterations, and it's a pretty time consuming and a tedious job. So the machine learning algorithms can be applied to do some learning on regressions, and you can either do learning on the full regressions or multiple runs of the full regressions. User can achieve multiple goals by applying these machine learning algorithms. They can improve the regression throughput by increasing the compression of their regression, or they can also use these machine learning algorithms to target some specific areas of the design, and also can focus runs on some specific desired behaviors that they want to target. The manual process of identifying and debugging these coverage holes takes a whole lot of iterations, and in all such areas these machine learning applications can help. It can also provide you with some analytics that can help in further test development also, right? So next I have shared some of the common ML use models here. These are some primary use models where users can take advantage of ML, but there can be some other use models as well where ML models can be used in industry. So one example is in regression compression. So this is often done to replace your nightly or your check-in regressions with a very high efficiency ML generated version. So if the full regression is significantly inexpensive, then the ML compressed regression can just augment or add to get more runs targeting the full coverage space. Note that this does not remove the full regression. It just reduces the frequency that the full regression will need to be run. Um, then you can also have some targeted regressions. There could be many different use cases for targeted regressions, such as creating a focus regression for some specific areas of the design that are getting large amount of code check-ins, or that are more susceptible to design changes, code changes, and more susceptible to bugs and all. Or users can also create the focus runs on low hit bins to increase some corner case scenarios and improve the coverage goals. Another application of algorithms could be in bug hunting or in the coverage closure. So users can have ML increase the hit rate of certain bins, and DV engineers can start backwards from the coverage holes and can add cover properties with some prerequisites. So increasing the hit rate of those prerequisites will improve the chances of hitting the holes faster. And you can also have these machine learning algorithms specifically create some models to target some failure scenarios also. So these were some couple of interesting ML applications. Uh, so now I'm going to cover the demo of these some applications, flows, and technologies with Cadence, Xcelium, and vManager tool. So I'll cover save restart flow with Xcelium, then I'll go to ranking and correlation with vManager. And in the last, we'll have some detailed slides or demo on the Xcelium ML flow. So save restart. So this methodology is very useful when you have, say, hundreds or thousands of tests in your regression, and most of these tests have some common initialization sequence, or you can say some boot up sequence. So in such cases, you can run the simulation to a specific functional point, or till that initialization is being done, and run any further tests uh, in the simulation can save on that and restart the simulation from that saved snapshot. So where your regressions have hundreds of tests which share some common initialization sequence, there this flow is very helpful, and it pretty much improves your regression performance if initialization time is considerably much higher and you have relatively smaller test times. It also helps in debugging the long simulation runs. You can identify some cyclic points and you can restart your simulation from those saved cyclic point and start debugging from there. So for an example, I've shown here, let's say we have some tests from test 1 to test n. So we can have test 1 just run the initialization sequence, then save the simulation snapshot, and then the other test from test 10, test 2 to test n can restart the simulation from that saved initialization point or the snapshot. This is an example where you can save the simulation at different cyclic points. So one thing to note here is how do we choose that cyclic point. So cyclic point should be long enough that the save overhead is low compared to the runtime, and should be short enough that if debugging a failure, you can quickly get to the fail point. You should also be able to keep enough snapshots to be able to walk back, and of course this would occupy some disk space. Now, how do we set up the save flow? So saving the simulation you can do either through Tickle or through HDL. So I've shown an example here. So in the right side, I have SV code where I have shown a configure phase. The configure phase has a sequence or an initialization sequence that consumes some time. And on the Tickle, if you see, I have put a breakpoint on the configure phase. I run the simulation till the breakpoint is reached. Then we can save the snapshot after the initialization is being done, and you can exit the simulation. You can achieve the same thing in HDL using the $save system task. Again, I have shown an example here where in the run phase, I have initialization sequence that takes some time. After the initialization sequence is done, I save the snapshot here using $save. Then I can override this base sequence while restarting in a restart.tickle file. I'll show that in the next couple of slides. Now, important thing to note here is that I would need a switch at elaboration and simulation time, which is minus process underscore save, which would enable our process-based save restart flow. Now, when we restart the simulation, we can have either a cold restart or a warm restart. Cold restart is usually the one that's being used mostly across the industry. So simulator can be re-invoked with a snapshot, and with the cold restart, you have the opportunity to change certain simulator invocation options and settings. Example, you can change the seed anytime, you can change the sequence, or you can run with the same seed. So if you see in the example, I've saved the simulation first, and then I can restart the simulation, and I have a tickle file here. While in the tickle file, if you see, I have a UVM factory override by type, where I override the base sequence with another sequence, which is the read modify write sequence. And I also change the seed to some other value and then run the simulation. Another restart that we use is the warm restart. So here in this case, if you see in the example, I have saved the simulation at different time points with a different name, like phase 1, phase 2, and phase 3, and I can restart from any of the saved simulation stages and can start the debugging from any of these stages if I want. Okay, so next I'm going to cover ranking and correlation in vManager. I'll cover what is ranking, how to rank runs in vManager, how do we enable parallel ranking, what is correlation, and how can we correlate runs using vManager. Right. So I'll show how to rank runs in vManager. How do we rank runs to improve the efficiency of your regressions? How to generate the reports to view this ranking? With ranking, you can remove certain runs that do not actively contribute to the coverage goals that you might want to achieve. You may call it as the process of dropping the redundant runs in your regressions, which do not add significantly to the coverage grade. So how ranking is performed? So you can perform ranking on your metrics or on the vPlan or the test hierarchy, and also from your runs table. So you need to first select the node from which you want to rank the runs if you are in the test hierarchy pane, or alternatively, you can also select the runs you want to rank from the runs table. So in case you are on your metrics page or the vPlan page, you can do following. You can select a single or a multiple items, say types, instances, bins, toggles, and you can do any of the following. And you can right click and just do the rank runs. Either you can select multiple items in the list tabs pane in the metrics page, you can right click and also do select rank runs, or alternatively, you can also select rank runs from the analyzer toolbar. Right, so in this case, if you see here on the analyzer toolbar, we have an icon to do a rank runs. So a window opens as below the rank runs window open. So you can select the metric model from here. So the metric model node can be selected. And if you see, I have a column here where we can add a new column name where I've added curve underscore something here. I hope it is visible. So next we can do is we can go to the verification metric or the metric model that we have selected, and optionally you can also select the cost if required and add the respective cost from the pull down list and just click on rank. Now this is the ranked report window that will open. So curve 24, if you remember, was the name of the column that we have given in the rank runs dialog box. And if you see, there's another column added which is delta underscore curve underscore something, which indicates the additional contribution made by each run to the overall coverage grade in comparison to the run listed above. And on the left hand side, if you see, is the name of the verification matrix or the node that we have selected. Right. Now, what is parallel ranking and how do we enable it? So ranking, if you would know, is a time consuming process which involves significant computation and heavy disk space. So in case you want to analyze many runs, you might have to wait long enough before you can analyze the rank results. So to save these times, you can accelerate the rank calculation by enabling parallel ranking in vManager. So there is also an overhead associated with it, such as distributed the ranking operation to multiple processes, process creation, communication, synchronization, and so on. So all these processes take some time. So as a word of caution, I would say here that we should enable parallel ranking only if you have your long regression environment and not in the small cases or small environments. Okay, so the next thing we move on is correlation. I'll cover how do we correlate runs in regression, how to generate reports after the correlation process. So you need to generate information on the contribution of each of your tests in the regression towards a certain coverage item. So this information would help you to debug or analyze certain coverage numbers, which you did not expect in your regression results. So correlating runs helps you see which runs in the context contribute how much to an attribute such as grade, sample space, or checks for a particular element in the V plan, including a section, coverage entity, or scenario, or a check. So how do we correlate runs? So in the test hierarchy pane, you can select the node for which you want to correlate the run. Then you can select the correlate runs from the analyzer toolbar. You need to select the entity for correlation, and after you select the required entity from the domain hierarchy, you need to click on the select button and a correlation window appears. You can view and review the correlated results page. So if you see here, I have on the analyzer toolbar just next to the rank runs as a correlate runs. You can click on the correlate runs tab and a window would open. You can select the metric or the model from your context window. So in this case, if you see, I have selected UART DUT. So once you have selected that, if you see on my right side, the UART DUT appears next to the metric model. Next, you can select the attribute. So I've selected in this case attribute overall average grade, and you can specify the column name that would appear in your report here. So next, you can also select some common attribute upon which the correlation has to be grouped upon. So I've selected past in this case, and next you click on the correlate button that you have. So this is how the correlation window would come after you have done the correlation. So on the left, you see the name of the node or the entity that I had selected in the metrics hierarchy, which was UART DUT. Now on the curve one, which I have given in the correlate run tab, you can see the same name specified here in the correlate runs dialog box. And the attribute is also shown, which was the path that we have selected. Okay, so next I'll move on to Xcelium ML. So I'll cover what is Xcelium ML, what the flow is, what are we trying to accomplish, and how do we do that. Okay, so I'll cover the overview of Xcelium ML. How do we set up and execute the regressions? How do we create learning models? How do we synthesize a regression? How do we generate and analyze the regression? So on a top level, Xcelium ML application will allow you to synthesize a new regression, and the new regression is supposed to meet some goals associated with coverage. So along with it, the tool provides analytics that can help you in further test development and further suggest or show some ways that you may be able to create interesting runs using ML. The way Xcelium ML achieve this is by monitoring um, at randomization points, and we are going to talk about these randomization points or the control points later in detail. So Xcelium ML monitors these randomization points, and then users can ask machine learning algorithm to generate some ML models. So these machine learning models are created for the coverage bins that you are targeting. So after you have created your machine learning models, you can synthesize the regression, focus on the goals that you may have. There are a number of analytics that help you understand what effects these randomization points have, how specific cover brains are influenced, how your regression is behaving. This is pretty much the high level of Xcelium ML. So next I have the Xcelium ML flow here. So users can run the regression with the ML interface of Xcelium enabled. So this is the lower portion of the diagram showing the Xcelium ML with the ML client. The data captured here is coverage and the randomization control data. You can start the Xcelium ML learning process. This process collects the data from the regressions and creates some machine learning models. Now, with the after the machine learning models have been created, we can generate the regressions. Now, the processes that you are running, they can be run in parallel to the regressions or further regressions that have been completed. The user invokes the Xcelium ML generation process with the user's goals, and the default goal is to regain the full coverage space. But we allow various customizations here. Users can target to some coverage specific goals that they might have. So the idea is to replace the directed test with a random test as much as possible. So this slide is an extension to the previous slide and cover in detail some of the application of the machine learning algorithms. So one is improving the throughput by compressing the regression, and this also improves your farm usage. So second is targeting specific areas of the designs to focus runs on some specific behaviors. So both are accomplished because Xcelium ML has the effect of increasing the hit rate of the target coverage. So if someone's are hit in 1 out of 500 runs in the original regression, they will likely be hit in 1 out of 200 runs in the ML generated regression, thereby improving the chances of hitting the different parts of the design and hence your coverage space. So when we talk about regression compression, this is often done to replace your nightly or your check-in regression with a high efficiency ML generated version. So if the full regression is sufficiently inexpensive, then the ML generated regression may just be added to get more runs targeting the full coverage space. And again, note this does not remove the full regression. It will just reduce the frequency that the full regression needs to be run. So you may have a regression which runs from say 5,000 CPU hours and you use Xcelium ML to compress to say about 1,500 CPU hours. That's the kind of high level goal that we typically want to achieve with these ML applications. Or maybe you are not looking at for say the full regression side, but you may want to create a check-in regression where you may want to have not the 100% regain, but you are looking at something say a 97% regain with say more compression of say 8x regain. Okay, so next application is the targeted regression. So you can also use ML applications to create a focus regression for some specific areas of the design that are getting large amount of code check-ins or design or code changes, and they are more susceptible to bugs. So users can create focus runs on the low hit bins to increase the corner case scenarios and improve the coverage space. Another application could be in bug hunting or in the coverage closures. This is taking the advantage of the fact that the Xcelium ML increases the hit rate of bins and can help find more bugs. The DV engineer can start backwards from a coverage hole and can add cover properties with some prerequisites, and increasing the hit rate of these prerequisites will improve the chances of hitting these holes. So idea is to have ML create a focus run for cover bins in your design. By doing that, you are increasing the hit rate of certain bins. Likewise, ML can learn from the failing runs and especially create models to target some failure scenarios or targeting some cousin bugs. So you kind of focus ML to increase the hit rate in those areas. Okay, so again, these are some applications where typically ML is being used. So I've shown here on the left example, a hypothetical example of a regression, which has a total of around say 5,000 runs, which is 50 tests, 100 seat per test, and which was around 5,000 runs. So the SV code that I have shown here is an example of a configuration object that is being randomized. So these configuration objects affect how the test behave. So each of the run of each of these tests contribute to some of the coverage space. So some bins are hit many times and this will be easier to recover or regain by ML, and some bins are rarely hit and these are relatively harder bins to regain by or recover by ML, while some bins might not be hit at all. So the hypothetical generated regression on the right, if you see, has around 1500 runs. So which is approximately 3.3x reduction, which is pretty much typical with Xcelium ML. So only some of these tests will be run and the number of runs per test will vary. The constraints are imposed by Xcelium ML, but only for the interesting configuration objects. There is a possibility where some of the bins are not regained due to randomness, while some of the new bins might be hit again due to the randomness of the ML generated regression. So what are the typical ML use models depending on your project stage? Okay, so the three stages that I'll talk about here are the early, middle, and the later project stage. So these are just the arbitrary stages, but are reflective of the general states of the projects that you might be working on. So you can, if you assume your project is in the early stage, so this is normally not much of the functional coverage in this state. So replacing your regression with the ML generated regression is not much recommended here. However, the augmentation can be effectively used and user can add runs to enhance the full regression and hit the failure cases much sooner. So if your project is in the middle stage, so at some point the coverage model is sufficient and the ML generated regression on this can be used for the nightly regression. So at this point, it is very likely that some runs will be added to the ML generated runs because those runs would have some specific or dedicated behavior that is not captured by the coverage model. This is also the stage at which bud hunting types of regression may add more value to the users. So next, if your project is in some later stages or the advanced stages, this is primarily the point at which compression that ML provides will be of most value to the project. So using machine learning algorithms to help close coverage can significantly save the engineering time. Okay, now this is the Xcelium ML flow. So first we need to set up the vManager for regression. Next, we set up or choose some randomization of the control points. We need to choose some coverage model of the metrics that we want to use, and we need to run the original regression to gather some data. Next, we create some machine learning models using the XML learn. Next, we configure the regression synthesis with the desired goals and run XMLGen to generate the synthesized regression. So once the synthesized regression is being run, we also generate a number of analytics using XML analytics to generate the sensitivity or regression analytics. Now these analytics can help you take decision on the further generation or changes to the regressions that you might want to ML to have. So how do we set up the vManager? So mainly Xcelium ML uses vManager for the following: to gather information from the regression runs, like you need to gather the CBB files, which is the coverage bit vector files for each run, the randomization trace files, which is the backdoor trace.txt files, the test name, test group, CPU information, and other statistics from the regression runs. vManager is also used to dispatch the parallel jobs for model interference, model creation. It is not necessary to use vManager as your regression runner, but we need vManager because we need for the above information, to collect the above information. So you can run your regressions, but the regression runs must be collected into vManager using the collect flow or some customer replay application that you might have. The Xcelium ML will generate the optimized regression in the form of a VSIF, which will need to be converted to the desired runner format that you might have if you are not using the vManager regression runner. Now, I've talked about the control points and the randomization points. So what actually are these control points and the randomization points, and how do we choose those randomization points and the control points? So you need to choose the randomization points or the control points that impact the simulation path. So usually the random variables that impacts the simulation path, the specific runs is going to take. So these are the variables or the objects which would often randomize once or a few times per simulation. Usually configuration objects are the good choices for the randomization or a control point, which so virtual sequences or some similar high level scenarios that can manage overall traffic also tend to be the good randomization point. So generic data items that are generally not good because they add a lot of noise to the ML, and which ML needs to filter out. Why do we actually choose these randomization or control points? Is to reduce the noise that ML might see and to improve the quality of your results. How do we so if you see the command here, we run xrun minus xlegend, then we provide the backdoor input file, which has the control.txt, which control.txt has the randomization points or the random points that we have chosen. Now, so there are cases where the engineers might not know the environment completely, and they might not know what are the interesting randomization points or the control points. So we have also provided a tool which is xmlgen backdoor config, which will automatically generate a backdoor config file if you do not know what are the good random control points, and let Xcelium ML generate those random control points for you. So this is specifically helpful in for the engineers who are not aware of what could be the best randomization or control points that I should provide to the Xcelium ML tool. So in that case, you can use this utility and you can generate a file here which can be provided to the learning XMML learning stage. So how do we run this utility? So first, you need to run a subset of your regression, say 1/5 or so, with a few seats per test in the AOX mode. The default output of this is the file which we call as SR backdoor input file single actions.txt file. Now we have a lot of recipes to run this utility. What example I've shown here is the recipe which is the most sensitive classes. So it will take this data and it will identify the classes that are more interesting and will dump out two files. So the output here are the two files. One is the SR sensitive variable classes.csv. So this has a table of classes that ML can learn from. Usually the classes that are randomized once during the simulation, and this number is usually not very huge. Also, it dumps out a file which is srvars to include file most sensitive classes.txt. So it's an example variable include file using the top sensitive actions. You can run with different recipes. So if you run with the recipe most sensitive action, it will generate a file which is the SR backdoor input file most sensitive actions.txt, and you can provide this file to the learning stage using XML, and this file can be provided in the learning.config file or the JSON file that you have. Okay, next we need to run the regression. So once you run the regression, the coverage needs to be turned on. So all the coverage that Xcelium ML must consider needs to be run as a part of the regression. The coverage data should be optimized. You can do that by settings, create optimized coverage data all to the session level of VSIF, or independently you can use this command create OPT curve data in the vManager while using the vManager collect flow. So the output of the regression is that might be used in the next couple of stages is the backdoor trace.txt file that is generated per run, and the CBB file, which is the optimized version of the UCD file per run. Next is how do we create the learning models. So we need to run the command xml-learn or the utility that will generate the learning models. So you may want to focus your learning on some certain coverage metrics, though your entire regression may have focus on all sort of coverage. So by default, we focus only on the cover groups, assertions, and the block coverage. So if you look at the model that I have shown on the right side, we have the utility, which is the xml-learn, which dumps out the machine learning models. So input to this is the test. You can provide the vmanager session ID that will incorporate all these tests. Then the backdoor trace file that was generated earlier per run, and also the coverage data, which was in the form of the CBB file, which is the optimized UCD file. Then you need to provide a learning configuration file, which is the JSON file here. I'll show an example of how the JSON file looks like, and this utility will create a learning model. So the command here I've shown is xml-learn, then minus config, which is a part to this JSON file or the config file, and the vmanager session ID for your test information. So this is how the JSON file looks like. So it has information about your server, the project, whether you want to dump extended dataset report, the test report, backdoor input file, engine params. So we have a different modes for engine params. If you have mentioned here, more effort fast, specifically if you want to focus on some rare ones. So user need to also specify the coverage matrix that they are interested in. So by default, we choose the type-based coverage and the cover groups assertions and the block coverage. You need to also specify the recursiveness if you want to have Xilium ML learn on the entire design or on the entire design hierarchy, or whether you want to go up deep inside those hierarchies or not. So all this information has to be provided in your learning.json. Fine. There are some more options that you can provide to xml-learn. So I've not added them here just for clarity. So this is an example of an output xml learn log file, how it looks like. There are some things that I have highlighted here. This So main thing to note here is the dataset summary here, which has information on the bins, bins covered with variants, runs, tests, then the randomness that the test would have. So this, let me explain what the bins here mean. So bins here are the total bins in the coverage model provided to xml-learn. So this number is usually impacted by the configuration attributes like coverage matrix or the refined files that your runs might have. Another thing to note here is the runs. Runs here mean the total number of simulation runs in the data set. Tests here are the number of the unique tests that you might have. The run to, usually we say the run to test ratio should be at least 5:1 for learning. Another thing to note here is the single assign action with variance. So this means the actions that vary only for one assignment in at least one run. And these are the actions that Xilium ML will use. Okay, so this is how the dataset report looks like, and this report is dumped in the reports directory. So this data here is something similar to what I have shown earlier in the learn.log, and it is slightly more than that. The important thing to see here is the bins hit by less than 1% of runs, which is shown by the proportion rare bins LEQ 1%. So these are the extremely hard bins to hit for ML, and machine learning may not be able to regain them more confidently, and the algorithm might have to work harder and may add more runs to hit these bins. So you really would not want to have high percentage of these rare bins. Also, this is going to affect the compression factor too, because the high percentage that you have here, the more runs will be needed to regain those bins, and this will affect the compression rate. Also, we have this graph here which shows how much randomness each of these tests and how much coverage space each test hits effectively. So x-axis here is the bin randomness, which shows what percentage of this test is bins this test is capable of hitting, and the y-axis, if you see, is the action randomness. That is the what percentage of these actions or influence these particular runs might have. So for each test, you will get this information. So the test on the right hand, if you have, these tests are more better for machine learning, but the ones that are at the lower bottom, they do not add much to the ML, and these tests are acting like they are directed. They may not be directed tests, but for ML, they are acting like the directed tests, and these tests are likely to be less useful for ML. Okay, so next is the XLM ML generation part. So the XML gen utility also takes a generation configuration file, which is a JSON file, which looks similar to the JSON file that we had provided to XML learn utility. So the input to this XML gen is the learning model that we have created. It also needs the original .vsif file because it will generate the generated vsif, which will have link to this original vsif file. So this is how the JSON file look like here. It has a reference to the learning directory, then the original vsif file, and the backdoor input file that we had. There are additional attributes of the switches that you can provide to the XML gen. You can use bin wildcard. If you want to target some specific coverage bins, you can also specify the maximum number of runs that you might want to have in the generated vsif. You can also specify if you want to use the incremental learning flow or not, or if you want to change the location of the reports directory or anything. So next we have the generated log from the XML gen. This is how the log file will look like. So I highlighted a couple of things here. So so mainly it looks at the test and the runs from the data summary. So if you are in the more effort mode, it looks at the deterministic bins that are hard to hit. And if you have more search bins, then ML will need more tests to hit those bins. So it generates 2 vsifs by default, and I have a third vsif here, which is the exploration vsif. This will be generated if we ask ML for it. But ML wants to be minimally invasive as possible and create a more reliable and accurate model for predicting and generating these high coverage bins here. So the number of runs here, the number of runs in the original regression, the number of tests here is the number of the unique tests. So srmin.vsif is the link to the minimal vsif that is being created here, which is sr_10.vsif. This is the vsif this corresponds to the hit where the curve, with the prediction curve, which I'm going to talk about in the later of my slides, where the curve starts bending here. And then we have sropt.vsif, that is the link to the optimal regression. This is where the prediction curve starts flattening. So I'll cover what is the coverage prediction curve here. The next one which I have here is the sr_exp.vsif. This is the exploration vsif, which corresponds to sr_1.vsif here. So this is a smaller regression targeting the low confidence bins from sropt, and compression factor here tells how many runs to the vsif to execute. So this example here, I have an example of a generated vsif. So if you see this, the first line is the include of the original vsif that we have. Then it will extend some test here, and then we show the test that is being extended. Then some of the constraint suggestions that it will have for each of these tests, and the backdoor mode here, if you note here, is CX here. So depending on how many constraint suggestions are there for each test will be run that number of times, and ML tries to be minimally invasive and only constrain some front-end knobs that too minimally. So this is how the coverage prediction graph that I was talking on in my previous slide look likes, and how the SR generated vsif correlate to this prediction graph. So when Xcelium ML generates regression, it creates a regain or a prediction graph. It's a kind of a logarithmic graph, and it gives prediction on how it's going to regain these bins. The more data you give to the ML, the more better the prediction is. So user can choose the number of runs they want to have, and that can get a good idea of what the coverage regain will be. The prediction graph goes up to 100% regain. In reality, that regain can be more than that, and the graph it can actually go over 100%. So in this example here, the original regression was around say 7,000 runs with 99% regain at around 2,000 runs that were achieved. So this will give you an idea of what you can expect from NML. Okay, so next is how do we analyze the regressions. So now that you have all this data and you want XML to analyze all this data, so XML has a bunch of features that can help you analyze the data. The user can use analytics for understanding the effects of the control points or specific coverage bins are influenced the overall behavior of a synthesized regressions. It helps you understand what area of the design you are not getting to focus on, also understand what area of the design you should not get that much focus, and let XML decide for you. So for analytics engine, you need the ML model or the data set, and also for some of the analytics, like for comparison purposes, you need the additional data set for comparison. Right. So sensitivity analysis and regression profiling comparison purpose are the main usage of these XML analytics. So these are some example of some of the analytics, but they can be more than just these examples. The sensitivity analysis, that's the first one, is showing the relationship of the random variables or the test bench features to the coverage bins. So the higher the bar is, the that is the most important test or variable for hitting the coverage. So the sensitivity analysis can be reversed by providing the test variables and asking what bins the test variable has most impact on. So this is excellent for a DVN engineer who is trying to figure out how to tweak their test bench to get better focus on some areas, on some specific areas that they want to target on. Okay, next is the run distribution. This just shows the number of runs of each test. So typically the original regression will be fairly uniform. The ML generated regression will have some variance and will highlight the test which ML deems as more useful, and the ones it doesn't think provide as much value. Next, we have the hit ratio chart that shows the bins on the x-axis, and then this percentage of runs that hit the bins on the y-axis. So I have two graphs here. One was generated on an original regression, which was on the which was around 10,000 CPU hours, and next is on ML generated regression, which was run for about 1,000 CPU hours. So each green dot here is a bin. So if there are around 100K bins, then you will see around 100K dots here, and you can hover over on these dots and can get more information. So important observation here is that the ML run the tendencies for everything to be shifted up or with a which has a higher hit rate. And another important point is that the bins at the very low bottom are extremely low probability bins, and ML will generally regain them. But these are the bins that run to run may not be regained due to randomness. Okay, so next is the sensitivity analysis. So if you see the sensitivity analysis, I have used the utility XML analysis with the switch minus sensitivity, and I've passed a switch which says minus top 10K actions, and the argument to that is 10. So when I run this utility, it generates a sensitivity.json file and also a sensitivity.html file, which gives you the top 10K actions that have the most influence on the machine learning. And with the top 10K actions, it also dumps the variable name, the importance of that action in the overall ML run. The bin's wildcard here indicated the wildcard filter was used or not. It also tells you the scope of that variable, the variable name, and relative importance of that variable. So there's a corresponding HTML chart that is generated for each action or each variable here. So the x-axis has the control point generated from the sensitivity.json file, and the y-axis here is the importance of the control point on the coverage. So the sensitivity analysis gives you the coverage bins compute control knob sensitivity. It also, or given a control knob, computes the coverage bins for which the control knob is most sensitive. The synthesized regression profile here looks like this. So you can generate a hit ratio and compare to the original regression. It also generates the distribution of test of the synthesized regression. Okay, so another usage is with the mainly for regression evaluation is using XML analytics with the minus eval switch, where you can do some regression evaluation and you can evaluate the original data set with the learning set. So this will generate following output. This will generate a stats.txt file. I'll show you how that file looks like, and it also generates some hit ratio graphs. So if you see the graph on the right, on the x-axis are some specific coverage bins, and on the y-axis are the percentage of runs that hit the cover point. So if you see, I'm not sure if that is visible, some of the dots here are green, some are red, and some are black. So green ones are the bins that are the recovered, the red ones are the non-regained bins, and the black ones are the newly hit bins here. Right, so the hit ratio graph it, are generated, so you can see different HTML files generated for the original hit ratio, the suggested hit ratio HTML file. You can have the original hit ratio mark knockregain.html. Also, there are some JSON files that are being dumped once you run this command. So you can have a file dumped with the newly hit bins. It will have information on all the newly hit bins that were not, so these are the bins that were not hit in the original regression. Then there's a JSON file dumped with the not regained bins. So this JSON file will have all the bins that were not regained. And you can also have a JSON file which dumps the hit ratio comparison. So this is how the output stat.txt look like. So on the first half, you have the summary from the original dataset. Then you have the summary from the ML generated dataset, and then there is a comparison. So if you see here, the original dataset has the number of bins 496. The resultant dataset also has the 496 bins. But if you see in the original dataset, the bins covered were 384, while in the ML generated set, if you see, the bins covered are 456. And this is because there are some around new 72 new bins that are been hit in this regression. And for the regression that I'm showing this data, they are 384 regained bins, and there are no bins which were not regained. Okay, so now very often a question comes up: how do we compare XLM ML with ranking? So ranking is a good technology, but it has its own limitations. And first of all, ranking can help you achieve 100% regain with a fraction of runs. It is simple to use. You have committed seeds, and there is no randomness there. And if we have seen that regain drops significantly once you have the random seeds. So since you do not have random seeds, you cannot explore new paths, and ranking is not resilient to any design or test when changes. So if you uh, have your ranked runs, and if you change the randomized seeds, then the regain will drop, as I will show you in the table below. But if we have seen that if you have your rank runs and if you make any design or test when changes, then those ranking is not applicable then. While with Xcelium ML, the runs are still random, so you can explore additional new paths. It will potentially hit new wins that are not been hit by the original regression. Can achieve 100% regain with a fraction of runs, and this is resilient to design and test when changes. It requires some CPU time to create some learning models. So the table down here shows how much the ranking regain will apply and will typically suffer if the seeds are made random. The point here is that the distribution of specific test, which is really what the ranking is not sufficient to get a good regain. While with Xcelium ML, we also account for how control type randomization affects the behavior. So it isn't just the test distribution, but also some specific constraint biasing that we are doing with Xcelium ML. Now we have seen cases where users have run ML regression and a rank regression side by side for say n days, where n is some arbitrary number that was chosen by the customer. So during that time, the design and the testament changes were checked in, and the rank regression typically shows significant degradation from its 100% starting point down to around 95% or 90%. The level of degradation depending on the amount and nature of the changes that were coming in. Whereas the Xcelium ML regression sitting next to the ranking regression typically retained its 99% regain, or it was very close to that. Next thing that I want to bring out is that we are working on an application or a tool that can analyze the customer environment and can evaluate the environment and give info on how good the environment to be considered for Xcelium ML. So it will look at some parameters like the randomness, seeds, and evaluate the environment. This is pretty much that I have with for Xcelium ML. So next, Sundar will cover some case studies on Xcelium ML.
Thank you, Anjan. Hello all. I will walk you through some of the case studies of ML adoption and the results of such adoption. But before that, I want to take you through some of the criteria of an ML-friendly environment, which can help you in giving you better ROI. Firstly, our Xcelium ML solutions primarily focus on an SVM based environment, and we are not focusing on other language coverage models as of now. And an environment which has some of the randomization control points which can have an impact on how a test behaves in the early stage of the run is much conducive environment than an environment where a data is randomized throughout the run. So ML can work on these control points and optimize the overall regression. And an environment which has more tests with different seeds, which can hit a higher variance of cover bins, is a much suitable environment for ML, rather than an environment where we have more number of directed test cases or unique tests or single seed tests which are hitting a particular bin. So ML doesn't have much to play with those environments where you can't optimize more. Whereas in an environment where you have n number of tests with m number of seeds, ML can work on it, optimize those tests and work on those constraints and give you a better compression in these cases. So these are some of the criteria where if your environment has these particular scenarios, definitely this environment is suitable for ML. There are still some more things there, but at least at the top level, these are some of the traits of environment which can be fine-tuned with using an ML. With this. So now there are various cases of using Xcelium ML. I'm just taking two main scenarios here. One, in typical DV environment, we work on either in the early or middle stage of project adoption. So this particular scenario is on a peripheral IP, where assume there is a version 1.0, which is more or less stable, and there is a next spec version or a version change is happening. And so you have a version which is stable, and you have the next version which is coming where assume like 10 to 15% or like max 25%, there is a variance in the spec. So already you have a base regression, assume which is having like 10,000 runs, hitting approximately some n number of bins. available, and you are going to add another 20-25% of coverage on top of this particular thing. So what are the purpose of using ML here? So first, can I augment ML to optimize this regression, which is currently like, assume some n runs are there. Can I optimize it to give me the same coverage, or like probably like 98 or 99% regaining of the original regression, but within n/3 or n/4 runs? That is one particular use case, and I can focus on only for the newer spec version changes. I can work with ML to fine tune that also to get a conducive environment. Whether can I get more new bins? When can I use ML? There's randomization to hit more bug hunting cases. So this is one particular scenario where I use ML. So I use the traditional approach. I use the regular approach for the version 1.0. I gather the data, coverage data, collect the coverage, and I use my ML to do a learning model on this particular base version. But this is not going to change much. This is already proven data, so I keep this. Whereas I go for the version 1.1, I do this incremental learning on this, because here I'm going to add more coverage bins and more randomization. I'm going to focus here. So I use ML to fine tune this particular environment and create an incremental learning model. So I'll combine these two models to get a more prompt model, and overall I'll use a more optimized regression suite. This is one particular case, and in this particular case, my primary focus is not the 100% coverage regain. So even if I'm getting 97-98% coverage regain of the original base regressions, I'm okay with that, provided it can give me a better regression optimization. So in this case, we had a very good regression optimization with 97% coverage regain. And the second case is where the project is more or less stable. I'm close to like hitting like 100%, like 98 or 99%. So now my primary focus is like, okay, instead of running new directed test cases, can I use ML, these randomized runs, can it also help me in targeting some of these corner case scenarios? Can it also help me in hitting some new bins instead of manually writing more and more directed cases? So this is another typical case. So here, my primary focus is not optimize the regression optimization, but more towards a stable regression with additionally using these randomized runs. If I can able to get some additional new bits, that is my primary that is my goal. So this is the other case study. So these two variants, most of the customers where we work with are primarily focusing on either of these two scenarios, and we had a lot of success stories. And the typical expectation with ML is in the ranges of like 3 to 5x, but that is with 98% of coverage regain. But if you are targeting more closer towards the 100% regain, then you can expect around 2 to 3x regression optimization. That should be your expectation. But whereas we can work on it, and in some of the cases we are fine-tuned. Even if you're getting like around 99.3 to 99.9, we have seen like gains like around like 4x, 5x in cases, 6x also in cases. So these are, we had worked with various flavors of the peripheral IPs or processor-based IPs and other things, and these are the results what we have, and these are more or less like a lot of customer results which we have. And apart from this, we also have one of our customer who is presenting his success story of using ML and how it has helped them in their optimizing the regression throughput. That is also being presented by the customer himself in the poster section. If you guys can take a look into it, you can hear like more data directly from the customer on how they had implemented and what is being done. So with these results, I come to an end of my session. And if there are any questions, we're ready to take. Thank you.
Hi, thank you very much, Anshul, Ankur, and Sundar for this very informative session on faster regression throughput and how it helps for improving coverage through this machine learning method with case studies and results. And we do strongly believe, which is a must need for this time to enable the bug-free silicon or bug-free design, I would say, and with faster TTM. So we do have some interesting questions. Probably I can moderate some of the questions to you all. The first one is in machine learning, any way to look the code coverage whole and trace it back and suggest some configuration combinations so that this approach or the tool can automatically able to cover those coverage holes through a constraint or not? This is one of the questions which comes out. Would you like to share your thought on this?
Yeah, Karthikeyan. So on a top level, I'll say XLM ML application, it allows you to synthesize a new regression, and the new regression is supposed to meet some goals which are associated with your coverage. So when I was talking about the demo part in the XLM ML, I said XLM ML achieves this by monitoring some randomization points, and these randomization points, once it's monitors, the user may ask ML to generate some machine learning models. So machine learning models that are created, they are created for the coverage bins that you are targeting. So if the coverage bins that you are targeting are the ones that it will try to regain. So we try to regain. So customers, so there are some customers that might want to have, say, 100% regain with, say, 4x or 5x compression factors, while there are other customers who might want to have more compression, but the regain that they want to have is, say, 98% or 97%. Now, depending on what stage your project is in, like if you are in early stages, you may want to use XLM ML to augment your regression runs. So at that point in early stages, you do not have much functional coverage. So you want the ML regression to find the more to improve the hit rate of the coverage space that you already have, or you want to find more bugs in your area. While if your project is in some of the middle stages, that's the stage that you'll want to use XLM ML more for the bug hunting kind of purpose. So like your uh, project is been in a middle stage and you are adding a more lot of code, making a lot of design changes, so you may want to have a focus regression on those areas of the design that you are doing more code check-ins, or you want to know there are some areas of the design that have very low hit rate. So you can use the analytics that ML regression provides you, and you can improve the hit rate of those areas of your design that you want to have. Now if your project is in a very last stage, that's the point that the compression that ML achieves is more useful to you, right? So in all, I'll say whatever coverage that your original regression was targeting, XLM ML tries to regain that part of the coverage. I hope that answers.
I would just like to add a couple of comments on this answer. I think ML such a strong technology. It can provide you a lot of use cases, and our customers, we have seen that have been using it in many interesting ways, many interesting use cases. So I really like this question, and the way Achal has explained, we already have showcased 3-4 use cases: bug hunting and coverage, targeting a coverage space, and optimizing the regression. So I just want to tell that yeah, definitely there are a lot of other interesting use cases for which XLM can be used.
Hey, thank you, Anshul and Ankur. Good to note that the user cases has been verified to improve the coverage whole as well or cover it, and depends on the project stage it can be used it appropriately. Good to note that, and probably this would help to team to kind of evaluate with their user cases and design to see where the optimism can be applied. Thank you for that inputs. So the next question I do see, when you say multi-core in a part of the discussion, does it mean using the CPUs on all core concurrently, or simulator will run them in parallel, part of the multi-threading environment? So how that efficiency is kind of comes out, that through this machine learning aspect.
Yeah, so for multi-core, our recommendation is that you should get access to the full socket. That means all the cores of a socket, and you run on that socket concurrently. The idea is if you have access to full socket, then only you will get the real acceleration. Otherwise, there might be a lot of processes which might not really give you good results. But again, this is based on there are a certain optimum number of cores also, which again based on the design type and other things we have seen, like maybe 8 cores might be optimum for you. So get in touch with us for your specific case if you're looking for a specific problem, and I think based on that design it might change. But yeah, the bottom line, the recommendation would be get access to the full socket.
Then Ankur, you will get a lot of offline ping then.
Yeah, I'm
on
okay
these
with that.
cases, because when when the audience are going to explore this option, then I think we may need. I mean, you may want to give that clear cut, aspects of using multi-threading option. The input to audience are, please get in touch with the Ankur offline for more queries as well. Anchal and Sundar as well. So I'm going to next one. Especially this is on gate level simulation aspect. When the random deposits are being used in gate level simulation, in case of save restart method, which is being used in GLS, does the simulation restart from the fixed seed deposit values, or how it can be taken care, part of the GLS aspects is concerned?
Yeah. So when we talk about save restart, we say we mainly use this for the test, which have some common initialization sequence. So you can save the simulation, run the simulation when the initialization is being done, and you can restart from that initialization sequence. There's one more, there's a powerful way which you can use to take additional advantage of the save restart. We call it a reseeding methodology. So you can use a random seed for the initial run, and you can save the simulation state. Now you can reseed and you can change the seed when the simulation is restored, right? So you can use a command like process save, and you can provide the seed value, and you can restore the simulation with a new seed also. I haven't talked about dynamic test, but we also have a technology which we call as the dynamic test, where the engineers are able to create a new test also. So you can apply the new test even to the saved simulation also. So in that case, you need to create a new system verilog package, and you use it to extend the snapshot also. Probably you can get in touch with us to explain more on the dynamic test also and how the reseeding methodology works.
Okay, thank you, Anchal. I have the follow-up question on the same thing. I believe that it would have been answered earlier, but still, in the save restart method, is it possible to use common initialized state across multiple tests? I think it's answered it, but again, you can add your more insight into that as well.
Yes,
yeah, so you can save the initialization state, and you can either run a new test also, you can run a new sequence also, or you can choose to run a same test also. So you can do it through tickle also. When you restart, you can you can override your sequence, you can override the seed values that you have, and you can restart the simulation from there.
Okay, thank you. Thanks, Anshul. It's clarified that. Hope it clarifies that query from the audience as well. So another one, it's what I feel is very critical for all of us. What would be the runtime difference on the regression run with and without enabling the ML clients? Do you have any data reference to, because one is throughput important, and how is that runtime efficiency? So you have any data references or insight on this?
I think we had shared in the last slide, I had shared the data of the CPU runtime, not just the overall throughput. But if you want to validate, I think there is one of our customers also presenting in the DVCon in the poster session. So probably tomorrow, you can see in one of the poster session, the real-time data, what customer has presented. So we have a very good acceleration, but what we are getting with ML.
And I can, if really we want to put a number, I can see you that we have seen results up to 5x gains also 5x. When you run without ML and with ML. So there is a significant gain. It can be even larger, but I'm just giving you a conservative number. Right? So
hope you have the pessimistic number you are giving it looks like as 5x. But again, I wish that it can be more as well. But again, would that be, is that with the target coverage, or to maintain between regression without regression, or with the increasing that coverage also? For example, 98 to 99%. Do you
it's a trade-off,
or is it with the apple to apple comparison you are giving us a 5x improvement?
Yeah, so it's a trade-off. As I think Achal explained, Achal can talk more about it. So there is a trade-off between the regain, the coverage regain, and the optimization that you want to target, the acceleration that you want to target. Achal, would you like to? I think you covered it.
I think
In your
I covered in the last thing. Like you can expect, I mean, the expectation is 3 to 5x with 98% of coverage regain, greater than 98% for sure. But if you want to move towards closer towards 100%, yeah, that then the trade-off is there. Yeah, that can be little lower than 5x. It can be, but definitely in the ranges of 3 to 5x. That is what we are seeing. But your expectation is 98% above. Then yeah, we can get more like 5x and more than 5x also. We in most of the cases we are seeing.
So typically we say we target somewhere around 3x to 5x is typically what ML targets is.
Okay. Thank you. And yeah, any improvement, whichever comes, which is critical at this point of time. Thanks for the details. Again, this another points which is comes out as a question, right? Any customer testimonial, you already pointed out one of the poster session, but still, is there any other customer testimonial is there who uses the Xilium ML based usage model? And do you have any future plan of increasing this 5x to 10x, 15x? Any in futuristic thought process you have it? Maybe this is, I added my input as well, so
Yeah,
you can add
so
your inputs.
yeah, so I would like to answer the first question. Yeah, we have a lot of testimonials. I think you can go to our website, or you can we can give you specific details, and we have some articles published in some third-party publications also, where our customers have talked about Xilium ML. We have some success stories published, and I'm not sure should I name those specific details here, but yeah, there are a lot of these testimonials and success stories. And so we have, if you really want those specific details, get in touch or just search on Google. You will, I think you will land on some of these success stories, because some of these are in public domains already. So I'm just not taking name, but yeah, definitely there is a customer paper also, which is, I think, in DVCon agenda, and there is a poster paper. You can see that also is a big testimonial. Right now it's going to happen there at DVCon. And the second part of question, yeah. So I think although Achal can talk more about it, and this is a continuous process. ML is, I believe, is a game-changing technology, and that's what I started my this tutorial with. And we believe there is a lot of scope, not only in acceleration, but a lot of interesting use cases. We believe it's going to be something which is going to change the conventional way we do verification. And we are working on that, not only increasing the acceleration, but bringing out many new interesting use cases. And not only we, it's basically along with our customers, we are finding interesting ways and interesting ways to accelerate it further. So it's a continuous process. And Achal, if you want to add, I think if anything, future.
Yeah, I think Ankur has already covered. It's a continuous process. This technology is evolving and we are evolving. So I think there's a lot more to see in future in this domain. Yeah.
Right. Thank you very much, Anshul, Ankur, and Sundar, for the very informative session, and for clarifying all the queries as well. Hope that particular paper or poster, which is using this ML, may have some good hit rate. Let's watch it out in tomorrow and day after. That's the input that we are giving it to audience as well. So thanks once again for your excellent tutorial sessions and wonderful information what you have shared. And with this, we are concluding our day one of DVCon India 2021 with these tutorial sessions. Then, thanks to all the authors and audience who have made this tutorial session as very much interactive and informative. Thank you very much, and we do look forward all of your presence day two tomorrow. Until then, thank you for all of us, and have a wonderful day.
Thank you, Karthik, for being a wonderful host.
Thank you, Karthik.
Thank you very much.